So in topic 9, you'll be taking the ideas from topic 4 a little bit further. We're going to start with simple harmonic motion. So you're going to be looking at the defining equations of simple harmonic motion in more detail and looking at energy changes. You'll be using the formulas to work out acceleration, velocity, and displacement using algebra, but also looking at the graphs. Okay, so we're going to review those graphs as well. You're going to be looking at the difference between kinetic and potential energy and looking at the interchange between them, and you'll also be looking at energy transfers. These are the relationships that you'll be coming across, and some of these are fairly familiar. Some of these we looked at in topic 4 last year, so we'll do a little bit of revision, and others will be starting and deriving from scratch. Now, although I will be covering some revision aspects in this short video, I do recommend that if you find it a little bit heavy going and you would like to revise the grade 11 stuff, you go to the slides presentation and you find the link to this video, which will cover everything on simple harmonic motion that we did last year. So what is simple harmonic motion? It's a type of periodic motion or oscillatory motion where the restoring force, F, is proportional to the displacement, but in the opposite direction. Let's have a look at this in more detail. A graph of displacement time for an object moving in simple harmonic motion, like for example a mass on a spring, is like this. The defining features of this graph are the maximum displacement, which is the amplitude, sometimes referred to as A0 or X0. The time for a complete cycle, which is referred to as the period, capital T. And the displacement, x, which in this graph varies to follow a sine function, which we'll come to a little bit later. Now back to this defining equation. All objects in simple harmonic motion follow this rule. In the case of this spring, the restoring force would be the force back up of the spring as the displacement is down. Okay, so as you can see, the direction of this restoring force is opposite to the displacement and thus the minus sign. Now, the constant of this proportionality is omega squared, which is the angular velocity. And we'll look at that a little bit more in a second. But it is exactly from the circular motion theory that we did earlier. Now, what does circular motion have to do with anything? Well, you can see this on the actual slide presentation, but an object that is moving in simple harmonic motion is actually also tracing out a path of a circle. And that's why the physics is interchangeable. So we can rewrite this defining equation as F equals omega squared x minus. And of course, because force is proportional to acceleration, we can also write that equation as acceleration equals minus omega squared x. So these three are just as valid. And here we have them nicely laid out. Now let's have another look at angular velocity or angular speed. If this motion is similar to that in a circle, then we can use the same ideas that we used in circular motion. So what is angular velocity? Angular velocity is how quickly an object traces out a circular path. So using radians, angular velocity would be 2 pi, a complete cycle, over the period t. We also remember that frequency, the time for one cycle, f, is 1 over the period, t. So now we can combine these two equations to give us a measure of angular velocity in terms of frequency. Omega equals 2 pi f. And now we have another relationship. So let's have a look what we've got so far. The two defining equations, 1 and 2, our relationship for angular velocity, 3, and angular velocity in terms of frequency. So that's 4 relationships that we can use. So there are 2 very specific cases for simple harmonic motion which are very common. One is the pendulum, and the second one is the spring mass system. So I'm just going to say a few things about each of these. Firstly, interestingly enough, the pendulum only follows simple harmonic motion for very small angles. There is a proof associated with this, but I'd rather you looked at it later. Okay. What do we know about the pendulum so far? Well, last year we did have a bit of a play around with the formula for period. T equals 2 pi square root L over G. Okay, where length was L was the length of the string and G was acceleration due to gravity. Okay, so you've used that formula before, and it can come in handy with more complex questions. And the spring system. Now, the mass spring system usually looks like this. It's usually a horizontal mass spring system, because vertically, although it's kind of more commonly viable, the restoring force up is kind of interfered with by G. So you'll always have a weight factor reducing this restoring force. So it makes the situation a little bit more complicated. So when we analyze spring systems for pure simple harmonic motion, they tend to be horizontally drawn like that. And there is also a similar relationship for period, which is square root of m over k. Okay, where k is the spring constant. Okay, so these two formulas are on the data booklet, so you don't need to learn them off by heart, but it's important that you are aware they exist and you understand each term. So a little bit later on, as you are breezing through your calculations and your questions, you might want to look at the proof there for the pendulum, which is in here somewhere in this video. If not, I can just explain it to you in a couple of minutes, but go through everything else first. So let's just recap a little bit. We've got our angular speed or angular velocity relationship related to simple harmonic motion. So we've got 2 pi over t and 2 pi f. What else have we got? And we've got all our defining equations. Acceleration equals minus omega squared x, and the associated variations f. And what I suggest you do now is just stop and have a look at all the questions up until here. So do questions 1 up until 10. Should only take you about 10-15 minutes maximum. And then you can carry on with the video. Okay, so now you're familiar with some basic ideas. I'm now going to look at the graphical solutions to the simple harmonic motion, which is basically looking at the sine function that this represents. Now I'm going to start off with just describing this graph. The motion in this situation starts with an oscillator which has zero displacement to begin with. Okay, that means whatever it is it's doing, it begins at its equilibrium position. I should have mentioned this earlier, but zero displacement is equilibrium. And as the force pulls down, for example, the displacement would be equal to whatever's on this function up until a maximum, which would be x naught, or sometimes in other books they write amplitude or a naught. Okay, so that sine function it looks like this: x naught sine omega t. Now there is another way of writing this. You could make a general statement, omega t plus a phase difference. Now what that refers to is that this formula here is specific to an object which begins at displacement 0. But that's not always the case. I will look at the situation where it begins somewhere else a little bit later. So right now I'm just going to talk about what happens when you start at displacement equals 0. So therefore you get a sine function. So what do we do with these? Well, we don't just want displacement, we want the velocity as well. So you guys know how to differentiate now, but to find the velocity, we would use the differential, dx over dt, okay, which gives us v, and this is from motion. So this is kinematics. So that's a really, really basic idea, but you can apply it to simple harmonic motion. And if we differentiate that function, we end up with omega x naught cosine omega t. So for an object which begins at its equilibrium position, we have x equals x naught sine omega t, and velocity equal to omega x naught cosine omega t. And we can go one further, because we know that if we differentiate velocity with respect to t, we'll get the acceleration. So the acceleration then would be omega squared minus x naught sine omega t. Which, if we have a look at our equation for displacement, again, this is a little bit of revision for you, but our equation for displacement is x naught sine omega t. And if we look at our statement for acceleration, we have an x naught sine omega t here, which gives us our solution to the defining equation for simple harmonic motion, which is up here, a equals minus omega squared x, because we are left with a equals minus omega squared x, because this is x indeed. So what have we got here? We've got three equations that we can use. We've got one for displacement, x. We've got one for velocity and one for acceleration. And this last one proves our defining equation. And we can look at those three graphs together. Again, it's a little bit of revision for us here, because we have our displacement graph, our velocity graph, and our acceleration graphs plotted together. And with respect to how to relate one to the other, it's important that you just always take into consideration this idea that the gradient of the displacement time graph will give you velocity. So when you're asked to compare, you're really just dealing with motion graphs. Okay, remember that the gradient of a displacement time graph will give you the velocity. So, for example, where the gradient is equal to 0 on a displacement time graph, as you can see here, the velocity time graph is 0. and etc., etc. So you will always get questions where they're asking you to make inferences from displacement time graphs about velocity, or from velocity time graphs about acceleration, and vice versa, considering the area under the graph. Okay, so that's revision. We're not going to go into too much detail now because that was a topic 4 thing, but do bear that in mind. So let's just review what we've got. If the displacement time graph has a simple sine shape, it can be described mathematically by the equations using sine. So therefore, we've got x naught sine omega t, omega x naught cosine omega t. And these are given in the data booklet. Now, interestingly enough though, it's only a sine graph. If you think of our object oscillating, if it begins at the origin. Now, you could just as easily, and I would say more commonly, displace an object from its maximum displacement point. So let's say, for example, a pendulum is released from its maximum point. You don't release a pendulum from its equilibrium situation. So in that case, what you would have is your beginning of the graph starting at x naught. Now that's no longer a sine curve, that's a cosine curve. So therefore you have to be very careful what equation you're using. If you start from a displacement or a maximum displacement, you must use the displacement function as cosine. So we would start with x naught equals x equals x naught cosine omega t, and then your velocity would be the differential of that, which is minus omega x naught sine omega t. Okay, so just bear that in mind. Another way of dealing with it is to just use a general term, which is omega t plus the angle. But for IB purposes, because these are in the data booklet, we're going to stick with these. Okay, so remember, if it's leaving from equilibrium, you use these functions. If you release the oscillator from maximum displacement, you would then use cosine and sine. Okay, so here we have some simplifications which are given in the data booklet. Okay, so we have first V equals omega square root of x naught, which is the amplitude squared, minus x squared, and x being the displacement at a given time. And this is just a simplification that we can look at in a second. And then we have a second one, which is the maximum velocity v naught occurs at the point where the object is moving through equilibrium position, okay, and v naught is equal to plus minus omega x naught. So we'll just do a quick proof for these. If we start with the statement for velocity equals omega x naught times cosine omega t. And what we're going to do is just square the terms, and now we're going to use a neat mathematical simplification, which is sine squared omega t plus cosine squared omega t. Can you see where we're going? If you think you can prove this equation now, stop it and do it yourself. If not, just follow me. We can substitute this into the v squared statement to give us v squared. So we get v squared equals omega squared x naught squared 1 minus sine squared omega t. I forgot a squared there, I just put it in now. Okay, so we multiply those out. Okay, so now we've expanded, we multiplied out the brackets, and interestingly enough, we end up with omega squared x naught squared minus omega squared x naught squared blah blah blah. Anyway, can you see this is equal to x squared? Okay, our first equation. Okay, so now we end up with v squared equals omega squared x naught squared minus x squared. Okay, so lo and behold, we are closer to where we're trying to go. If we square root everything now, we end up with V equals omega square root of x naught squared minus x squared. Okay, so that is our equation there for velocity, and it gives us a little shortcut. Now, when x, if we look here, the equation confirms that the maximum velocity will occur when the particle is moving through the equilibrium position. So when the equilibrium position happens when x is equal to 0. Okay, so if x is equal to 0, we are left with the square root of x naught squared, which is the amplitude squared, remember, and we square root it to give us this. So that's the two sneaky, easy formulas. I would definitely try doing up to question 16. Now, if you can, take about 10 minutes to practice, and then we'll go on to energy. Right, there's definitely light at the end of the tunnel. We are very close to finishing this section. We're just going to look at energy during simple harmonic motion. So let's think about our oscillator. And as it's moving, we need to consider potential and kinetic and total energy of an object moving in simple harmonic motion. Now, if we can consider a pendulum, which transfers potential energy to kinetic. And what happens then? Well, at maximum displacement, you have maximum potential energy, and at zero displacement is when the velocity is going fastest, as it's going through that equilibrium point, is when all the energy becomes kinetic. So as you can see, you are constantly cycling between a maximum gravitational energy to a maximum kinetic, and somewhere in between you've got a bit of both. Now the total would be equal here to the gravitational and here to the kinetic. Now in a spring system it'll be the same, but and let's do it horizontally, because if you do it vertically it will become a real mess. So if we do a horizontally oscillating spring system, we are oscillating between strain energy as you squash this spring. So as you squeeze the spring inwards, you've got maximum potential energy again, but this time it's strain energy or elastic energy, E. So there you've got your maximum as you've squashed this spring. That would be your maximum. And then as you release the spring and it lurches through that center position, that's when the object is moving at its fastest point, and that's where it's got the most kinetic energy. So again, you are oscillating between having maximum potential and maximum kinetic, and that's what this graph represents, that cycle. So within one simple cycle, so that would be x naught maximum, so here to here, okay, you go from having maximum potential energy and then having maximum potential energy again at the end of the cycle. So your potential energy goes from a maximum here down to a minimum where the displacement is 0 as it goes through there in the origin, and up again up to a maximum. And your kinetic energy does the opposite. So your kinetic energy starts off being 0 at maximum displacement, increases to be maximum there where the displacement is 0 up to there, and then decreases again down to 0. And then our third function is the total energy. The total energy there, which is what you get when you add them together. Okay, so let's have a look at that in terms of equations. It's really quite simple, because we know, for example, kinetic energy is equal to a half mv squared. But we also know that the velocity of an oscillating object, we know this now, is equal to plus or minus omega x naught squared minus x. So if we put that into our kinetic energy function, we will square it, so we will end up with a half m, and there it goes. Okay, so this is how we calculate the kinetic energy of an object moving in simple harmonic motion. Now, just for fun, we're going to look at what happens when we have the total energy, and we're going to actually come up with an expression for the potential energy. Like I said, it's not given, but I think you should do it just as an exercise. So let's have a look at the total energy. If we have a look at this graph here, the total energy given, BIM, will be equal to the kinetic energy when x equals 0. Okay, so if we substitute that into here, we know that x equals 0 at that point. We will end up with the following equation. So Et equals a half m omega squared x naught squared, the amplitude squared. So that's our total energy. And that's our second energy equation. Now, how do we work out the potential energy? Well, we know from here your potential energy equals the total energy minus the kinetic energy. Okay, so if we consider this situation. So let's write that down using our fancy equations that we've already derived. Here we go. So our function for total energy, where we're just using amplitude, and our function for kinetic energy, which was up here. Now, if we simplify this, we've got lots of common terms on both sides. Okay, we have gotten rid of half mass omega squared and put them outside the brackets here, and we're left with x naught minus x naught squared minus, but it's minus minus, plus x squared. So if we simplify that, we end up with a half m omega squared x squared. So there we go. That's our expression for the potential energy of an oscillator. So that's pretty much it for simple harmonic motion. It's time for you guys to have a bit of fun with some more questions. Next lesson, interference and diffraction again.